Welcome to Module 1.3, Building Consensus Within Blockchain Networks. Now that we've seen how transactions are authenticated and blocks are created, let's take a closer look at how all of this data is reconciled across large networks of nodes. We talked about the basics of nodes and consensus mechanisms in our beginner course, and now we'll look deeper into how consensus is built on blockchains. Anyone can run a node and keep a record of a blockchain's data as long as they have an adequate computer and internet connection. A node is a computer or server that validates and stores the transaction and block data of a blockchain network. As of April 17, 2023, there were 17,592 reachable nodes in the Bitcoin network across the globe. However, networks that are supported by tens of thousands of servers storing the data can run into a few challenges. Distributed ledgers like the blockchain suffer network latency issues that create temporary inconsistencies. Most critically, two or more nodes may create valid blocks at approximately the same time, resulting in a temporary fork in the blockchain, or some nodes may behave maliciously. As we've learned from our beginner course, a robust blockchain network should be Byzantine fault tolerant. This refers to the blockchain's ability to continue operating even if some of the nodes fail or act maliciously. Blockchain technology employs consensus mechanisms to facilitate agreement among all participating nodes on a single unified version of the blockchain. There are many different types of consensus mechanisms. Let's use Bitcoin's proof-of-work consensus mechanism as an example to demonstrate how this mechanism works. First, users create transactions by digitally signing messages indicating the transfer of Bitcoins from one address to another. Then, these transactions are broadcast to the entire network and enter a pool of pending transactions where they wait to be processed by miners. This transaction pool is called a mempool, short for memory pool. Miners collect unconfirmed transactions from the network's mempool and verify them, checking for double spending and ensuring the digital signatures are valid. Miners prioritize transactions that offer higher fees in order to maximize their profits. Next, miners group the verified transactions into a data structure called a candidate block. Miners then compete to solve a cryptographic puzzle to find a hash value below a specific target. This target is determined by the network's current difficulty level. Bitcoin's difficulty level is set to maintain its block time of roughly 10 minutes and is adjusted automatically after every 2016 blocks, which takes approximately 2 weeks. This mining process requires significant computational resources and energy, which is why this is called proof of work. The first miner to solve the puzzle broadcasts the winning nonce to the network. Other nodes then verify the new block by ensuring the block's hash is below the target and confirming that the transactions included in the block are valid. Nodes then remove the transactions included in the block from their mempool. The winning miner receives a block reward in newly minted Bitcoins and the transaction fees from the transactions included in the block. This reward is what incentivizes miners to participate in the proof-of-work consensus process. Lastly, the entire network needs to reach what's called finality. Two nodes could have solved the puzzle and created a valid new block at the same time. When this happens, the longest chain principle dictates that nodes always recognize and build on the longest chain. Over time, the network converges on a single version that's the longest chain as more blocks are added to it. It's generally considered safe to consider transactions final after 6 more blocks have been added to the Bitcoin blockchain. This is called a confirmation. Another prominent consensus mechanism is proof of stake. The Ethereum network switched from proof of work to proof of stake in 2022. Instead of relying on miners committing computational power, proof of stake relies on validators staking their cryptocurrency to secure the network. Proof-of-stake systems typically choose a limited number of validators to validate blocks, whereas proof-of-work systems encourage as many miners as possible to compete to validate blocks. For example, Ethereum validators must deposit and lock a minimum of 32 Ether as a stake to ensure they behave honestly. Validators that stake more Ether stand a better chance of being chosen to validate blocks and earn rewards. The beacon chain, which serves as Ethereum's consensus layer, is responsible for selecting validators, organizing them into committees, and coordinating the consensus process. A validator is randomly selected to propose a new block within each committee. Other validators vote on the block they believe to be the most accurate. A block becomes finalized when a sufficient number of votes or attestations are collected. In Ethereum's proof-of-stake consensus mechanism, validators are rewarded in staking rewards and transaction fees by proposing and attesting to blocks in proportion to their staked Ether. Validators who fail to participate or act maliciously can lose a portion of their staked Ether as a penalty. It's important to remember that consensus mechanisms employed by blockchain networks are subject to updates and modifications over time. Aside from proof of work and proof of stake, there are several other alternative mechanisms that have gained popularity. Delegated proof of stake works by electing a fixed number of delegates responsible for validating and adding transactions to the blockchain. These delegates are incentivized to maintain the network's integrity and can be voted out by stakeholders if they fail at this task. Proof of authority relies on a limited set of trusted nodes, known as authorities or validators, to validate transactions and create new blocks. These nodes are usually selected based on their reputation, expertise, or other criteria. This consensus mechanism can be highly efficient and scalable because it's more centralized. Each consensus mechanism offers its own set of advantages and trade-offs when it comes to security, decentralization, scalability, and energy efficiency. Proof of work has come under scrutiny due to its substantial energy consumption, while proof of stake offers a more environmentally friendly option but has its own drawbacks, such as centralization risks, in which attackers acquire old private keys that once held a large stake to create a fork, is one risk that proof of stake is more susceptible to. Let's put everything we've learned together to see what makes blockchain technology special. Imagine the blockchain as an upgraded and sophisticated digital version of an accounting book. The distributed digital ledger records transactions, the transactions are grouped into blocks, and these blocks are chained together to form the blockchain. Each component is made tamper-resistant and secure by cryptography and game theory, applying numerous concepts and functionalities such as public key cryptography, hash functions, digital signatures, Merkle tree and Merkle root, and consensus mechanisms. The result is a decentralized, transparent, and secure system that allows users to send and receive digital assets or information without the need for centralized authorities, such as banks. The blockchain offers a wide range of advantages over traditional systems and represents a groundbreaking shift in the way digital assets and information are exchanged and managed without the need for a trusted intermediary. Ultimately, it empowers individuals and industries toward a more efficient, open, transparent, secure, and equitable digital future. In the next module, we will explore the various types of blockchains and different blockchain layers.